Assalamu alaikum. Dear students, I welcome you to 45th and last lecture of probability and stochastic processes. Since the first lecture, we have come a long way, and in this journey, we have discussed many mathematical ideas and their applications to probability theory. Probability theory, which is used to analyze unpredictable phenomena. We covered basics of probability theory, then we moved on to discussion of random variables and their characterization using probability density function and cumulative density function. Then we moved on to other types of random variables, from discrete to continuous to those pairs of random variables defined on a plane. And we also talked about transformation of different random variables and their applications to different problems of real life. We covered a major application area of probability theory, that is stochastic processes, where a random, unpredictable, time-varying phenomenon is observed and its behavior is analyzed using tools of probability theory. We started the discussion of stochastic processes with Markov chains, where this unpredictable time-varying phenomena is sampled at discrete, pre-planned, and usually regularly spaced time intervals. And we also restricted the values that this unpredictable phenomenon can take, and they formed a finite or countably infinite set. We extended these ideas to those cases where the transition, the change, takes place not on predefined regularly spaced time instances but at any time, and we call that continuous time Markov chains. We have been working with this continuous time Markov chains for last 2 lectures, and today we are going to conclude our discussion of continuous time Markov chains. To review what we were covering in past couple of lectures, let's quickly see what continuous time Markov chains are and where they can be used to analyze a time-varying unpredictable phenomenon. Let's have a look at time-varying phenomena, that is the number of customers in a queue. You can also assume that this represents number of customers inside the store. So customers come in and they come independent of each other and then they leave. So total number of customers in a queue, if there is a queue, or inside a store, can be modeled with continuous time Markov chains, because the change in number of customers in the queue or the change in number of customers inside the store happens at not regularly spaced intervals but at any possible time. So let's have a look at the graph of this type of time varying phenomena. The graph that you see represents number of customers in a line. At time t0, we start our observation and there are no customers till time t1. At t1, one customer arrives, and at time t2, another one arrives, and at time t3, another one arrives. Then at time t4, one leaves, at time t5, another one leaves, at time 6, another one leaves, and we have this line empty. And then at t7, another one arrives, and so on. To analyze the behavior of this type of time-varying random phenomenon, we decided that we are going to look at the arrival process separately from the departure process. So the arrival process for such a phenomenon looks like this graph, where at time t0 there is no customer, at t1 one arrives, at t2 another one, at t3 and at t4. So as the time progresses, more and more customers arrive and either join the queue or enter the store. To analyze this type of arrival process in a meaningful manner, we have to make a few assumptions. These assumptions are: customers arrive one at a time. That's our first assumption. The second assumption is that average rate of arrival remains constant throughout our observation interval, and that rate is lambda customers per second or any other unit of time. The third assumption is that probability of arrival in a very small time interval delta t is lambda times delta t. And the last assumption is that customers arrive independent of each other. So if one customer arrives now, it's not going to affect the arrival times of other customers. Under these assumptions, when we analyze the behavior of this arrival process, we can be interested in many things. For example, what is the number of customers when we observe this arrival process for time duration that starts at 0 and ends at a certain time instance t? We represented that with a random variable capital X with index t. And we found the probability of this capital XT taking certain values, that is number of customers, and we found that the probability of this random variable, number of customers that arrive in observation interval 0 to t, comes out to be e raised to power minus lambda t times lambda t whole raised to power k divided by k factorial. And this probability distribution of capital XT taking on a value k is a Poisson distribution. We could also be interested in the arrival time of a certain customer, 7th, 10th or 25th customer. That time arrival of kth customer, capital Y k, is also a random variable which is defined as minimum value of t such that xt has taken a value of k. And if we subtract the arrival time of kth customer and the previous customer, k minus first customer, then we have inter-arrival time, and that is also a random variable. So if capital T with index k is the inter-arrival time between k minus first and kth customer, then probability of this capital Tk being larger than a certain value of time t is e raised to power minus lambda t, and this inter-arrival time follows exponential distribution because this is 1 minus the CDF and this is opposite of CDF. In CDF we take tk less than or equal to the parameter value. Here we have taken larger than, hence we have only e raised to power minus lambda t. For this arrival process, we have found probability distributions of two random variables that describe this random process. But we need to know more. We need to know the dynamic behavior, how this arrival process changes. At what instance does it change from a state where there are k minus 1 customer to a state where there are k customers. So to analyze this type of transitory behavior, the transitions from a lower state to higher to higher to higher state, we need to know what is the rate of change of probability, the transition probability. We know that when we start our observation, then there are no customers. So at time 0, the number of customers being in the queue or in the store is always 0. So probability of capital X at 0 being equal to 0 is 1. So you start with this, and then as the time progresses, it goes above 0 value, then in short time interval, probability of an arrival is lambda times delta t. So as the time progresses, probability of arrival of a customer increases. It's not guaranteed that a customer will arrive in a certain time, but as the time progresses, the probability of arrival keeps increasing, and probability of this random process staying in the starting position, that is 0 customer, it keeps on decreasing. It starts with a value of 1, that at time 0 there is probability of 1 that there are 0 customers. But as the time goes on, probability of having 0 customer decreases and probability of having 1 or even more customers increases. But we are going to analyze it for a transition from state 0 to state 1, that is arrival of first customer. Let's have a look at the equations that describe this transition. So we are going to follow this notation that probability of capital XT being equal to K will be denoted by P, K with index K and then T in the brackets. And these are the starting conditions. At time 0, number of customers being equal to 0 is 1, and for time values larger than 0, probability of number of customers being equal to 0 is going to be less than 1. Let's see the probability of state change from K minus 1 to K, that is from 0 to 1, 1 to 2, 2 to 3. So if previous state at time t is K minus 1 and the next state at time t plus delta t is K, it has increased by 1, then the value of this probability is lambda times delta t. We assume that in short interval of time delta t, the rate of change from K minus 1 to K, the probability of this transition happening is proportional to delta t and its value is lambda times delta t. And what's the probability of this random process staying in the same state as it was at time t, that is having K minus 1 customers? That is 1 minus this probability. So there are only two possible events, that in delta t time either one customer arrives and state moves from K minus 1 to K, that happens with this probability, and the other event is that the customer does not arrive in time delta t and random process stays in state K minus 1, and probability of that is 1 minus lambda times delta t. This type of transitions can be modeled with a graphical representation, and that representation is shown on your screen now, where from state 0 to state 1 the transition probability is lambda times delta t and the probability of staying in state 0 is 1 minus lambda times delta t. These values are also applicable to other states because this arrival process behaves the same way no matter how many customers are already there in the queue. So this transition from 1 to 2 or 2 to 3 has a probability of lambda times delta t, and it depends on the delta t value, and probability of staying in state 1 and staying in state 2 etc. is 1 minus lambda times delta t. These transition probabilities of lambda times delta t and 1 minus lambda times delta t capture the rate of change from a state K minus 1 to K. But what is the probability that we find a certain number of customers at a certain time? We are interested in finding that. To solve for that, the probability of finding a certain number of customers at a certain sampling time, we need to find the probabilities of finding this random process in a certain state. To get that probability, we'll need other information, and that information is the probability of this random process being in the previous state and the probability of transition to the next state. Let's have a look at that expression which relates these transition probabilities and probabilities of finding the random process in a certain state. So probability of finding K customers at time t plus delta t, it depends on four things. What's the probability that there were K customers at time t, and the probability of transitioning from K to K, that is remaining in state K, plus probability of this random process having k minus 1 customers or being in state k minus 1, and then transition probability of moving from state k minus 1 to state k. If you expand all these terms and combine like-minded terms on one side, you will get this kind of expression which says that the incremental difference in probability of finding this random process in state k at time t and then at time t plus delta t, that is incremental change in the probability. And if you divide it with delta t, you get this expression. And if you take the limit and take this limit over this delta t and force it to go towards 0, you will get this as rate of change of probability of finding this random process in state k at time t, which is shown here that p dash with index k at time t is equal to this, which relates this rate of change delta and probability of this random process being in previous state k minus 1 and in the current state whose rate of change with respect to time that we want to find. The last relationship that you saw that tries to relate the probability of this random process having a certain state at time t and then changing that probability in incremental time, very small time delta t, and then taking limit on this delta t, converting the difference of two probabilities at time t and time t plus delta t into a differential, into a rate of change. So with this differential of probability of this random process having k customer at time t being on left side and other constant values on the right gives us something which is a differential equation. You can certainly solve this type of differential equation if you know the initial conditions. And you certainly know the initial conditions, which are that at time 0, probability of having 0 customers is 1. And you can use this initial condition and this simple differential equation to solve for probability values of being in certain state at a certain time. Let's solve for the first state, which is state 0, that is if there are 0 customers in the queue or in the store. So the initial condition is that P0 with 0 is equal to 1, that is at time 0 the probability of having 0 customers is 1. And if you plug in all the values for this P0 as a function of time and look at this differential equation, you will get the solution, which is that P0 probability of having 0 customers as a function of time when time goes above the value of 0 is e raised to power minus lambda t. All I have done is I have solved this simple differential equation to find the time varying property of this P0t. So probability of having 0 customers as a function of time has an expression which is e raised to power minus lambda t, where t0 probability is 1, and as time goes on, probability of having 0 customer with still time going on goes down, and probability of not having 0 customers start from 0 at t is equal to 0 and it goes up. So as time goes on, probability of having first customer increases and probability of not having the first customer decreases. You can certainly solve for probabilities of other states, and if you solve using the ideas of differential equation, you get this expression that probability of k customers being observed at time t is given by this, which we have already seen is a Poisson distribution. So this arrival process can be analyzed using this idea of rate of change of probability of a certain number of customers as a function of time. You can combine the arrival process with corresponding departure process and then you can model the behavior of number of customers in the queue or in the store. But we are going to present this combined problem of customers arriving and leaving as a general problem, which is called birth and death random process. In birth and death random process, there is a population, and that population grows because there are some births happening, or it goes to a smaller value because there were some deaths that occurred. So this population can grow or can become smaller as the time progresses. If we want to analyze this birth and death type random process where population can grow or can decrease, then we have to make a few assumptions so that this analysis is easy to perform. These assumptions are shown on your screen. The first assumption is that population increases or decreases by no more than 1. So if the change happens, which can happen at any time because this is again a continuous time Markov chain, but that change is going to be by 1. So if there are k individuals in the population, at next change the number of individuals in population could be k plus 1 or k minus 1. They cannot jump by a number 2, 3 or any other larger number. The next assumption is that birth rate lambda k may depend upon the current size of population. In arrival process, we assumed that the arrival rate remains constant and it did not depend on number of customers in the queue. But here, in general, lambda as a function of k can have different values for different values of k, which is natural because if there is a large population already there, k is large, then the birth rate, the chances of adding another individual in a certain amount of time will be large. And similarly, the death rate mu k may also depend upon the current population size, which is also natural. If there are many individuals and the chances of someone dying in a small time interval is large if there are more people in the population. And births and deaths occur independent of each other. Under these assumptions, we can analyze this general birth and death random process, and we can find different characteristics of the behavior of such a random process. For this type of general birth and death random process, we are interested in finding the probability of having k individuals at a certain time. But this number of individuals at a certain time may change. The question is, how do they change? Suppose a birth occurs and at time t there are k individuals. So what's the probability that a birth does occur between t and t plus delta t? Of course, that is going to be proportional to delta t, and the birth rate at k, when there are k individuals, the birth rate is lambda k. Then probability of moving from k to k plus 1 individuals is lambda k times delta t. Similarly, what is the probability that a death occurs when there are k individuals? Of course, probability of a death occurring from t to t plus delta t when there are k individuals at time t is mu k times delta t. So these are the transition probabilities. We are going to combine these transition probabilities with probabilities of neighboring states to find a general expression which will give us an expression for probability of finding this type of random process with value k, with k individuals being in the population. Let's have a look at these expressions which relate these transition probabilities and the probabilities of neighboring states and relate them to probability of the state we are interested in. So the two transition probabilities that we are interested in are moving from k minus 1 to k, that is a birth occurs and probability of that happening in time delta t is lambda k minus 1 time delta t, the birth rate at time k minus 1, the time when there were k minus 1 individuals in the population. The other transition probabilities we are interested in is a death when there were k plus 1 individual. So the random process moves from k plus 1 to k, and probability of this transition is mu with an index k plus 1 times delta t. These two transition probabilities tell us when things change, but it's quite possible that in a given time delta t, the population does not change. What's probability of that? Probability of that is definitely 1 minus lambda k times delta t and minus mu k times delta t. That is the transition probability of remaining in state k from state time t to time t plus delta t. Let's combine these three transition probabilities with probabilities of three neighboring states to find an expression for the rate of change of pkt. I hope you can manipulate all these terms and get this expression which says that rate of change of pk at time t is equal to lambda k minus 1 times probability of having k minus 1 individuals at time t plus mu k plus 1 times probability of having k plus 1 individuals at time t minus this lambda k plus mu k times probability of having k individuals at time t. This is another differential equation which relates the rate of change of pkt in terms of other known values, which are probabilities of being in neighboring states and probabilities of moving from neighboring state to this state. You can certainly solve this type of differential equation with a known value of initial conditions, and I'm not going to do that. I leave it for you as an exercise to solve this type of differential equation for analysis of a birth and death type random process. What I'm going to do is I'm going to tell you a few applications of this general birth and death process and how these applications can be analyzed and results can be summarized which are meaningful. The first application of this general birth and death random process is a simple arrival process. Here all these lambda n or lambda k are constant. We have assumed that in arrival process the rate of arrival is going to remain constant. Hence all these lambda n's are same as the constant arrival rate lambda, and there is no departure. For all values of n, the rate of departure to a lower state is 0. With these values of lambda n and mu n, you get your simple arrival process. The next application of this general birth and death random process is a queue, where customers arrive in queue, they get what they want and then they leave the queue, or they come to a store, purchase something and then leave the store. The graphical model is shown here, and for this type of arrival and departure process, the simple assumptions are that lambda n is always equal to a constant arrival rate lambda, and mu n, which is the customer dependent departure rate, is also constant equal to mu. So all lambda n's are lambda, all mu n's are mu. So this type of queue or store can be modeled with a constant arrival rate lambda and a constant departure rate mu. The next application of general birth and death process is, in that case, lambda n's and mu n's can have population dependent values, but there are two special values of mu 0 and lambda 0 being equal to 0. That is, from 0 the population cannot grow, and from 0 population cannot further go down. So when the extinction occurs, the population cannot grow and it remains there, it cannot go even further. So this type of population growth and reduction can be modeled with general birth and death process. So this general birth and death random process can model simple arrival process, arrival plus departure process with constant arrival and departure rates, or other types of simple continuous time Markov chains where transitions do happen and the rate of these transitions can be population dependent, or it can have an extinction where the left side state is an absorbing state, and once this random process reaches that state of zero population, it just stays there. The kind of analysis that we want to perform on continuous time Markov chain is similar to the discrete time Markov chains. We want to find out if a certain Markov chain is recurrent or transient. If it is recurrent, then all the states are visited again and again. Now, we don't know when they will be visited exactly, but these transitions will happen sometime at any possible time, and these states will be visited. And if the continuous time Markov chain is transient, then the states will be visited only finite number of times and then they will never be visited again. I hope you can see that a simple arrival process is a transient continuous time Markov chain, because as customer keep on arriving, you never go back to the previous state. The state that you are in always goes from k to k plus 1, k plus 2 and so on. But the arrival and departure process and other processes, they can be transient or recurrent depending upon the parameters, the arrival rate and the departure rate. I'm not going to actually do this analysis for you. You can consult a textbook for that, but I'm just going to present the results. That is, for a general birth and death type random process, which is a continuous time Markov chain, this chain is transient if a certain condition is satisfied. Otherwise, it is recurrent. So let's have a look at that condition which tells us if this birth and death random process is transient or recurrent. This condition is shown on your screen. The condition is that you sum an infinite series, and in that series the terms are shown here. You start with mu1 divided by lambda 1, that will be your first term. So you always start with 1 index for mu and lambda and you move to n. So first term is mu1 over lambda 1. Second term is mu1 times mu2 divided by lambda times lambda 2. And the third term in this summation is mu1 times mu2 times mu3 divided by lambda 1 times lambda 2 times lambda 3. And nth term is in the numerator multiplication of n mu's and in the denominator multiplication of n lambdas. So you continue to form these terms and keep on getting this summation to infinity, and if this summation is less than infinity, a finite number, then this continuous time Markov chain modeled by a general birth and death Markov process is transient. And if this number happens to be infinity, then this continuous time Markov chain is recurrent. We can apply this condition to check if a certain continuous time Markov chain is transient or recurrent. I just told you that a simple arrival process is transient. Once you are in state k, you move to state k plus 1, you never come back to state k. What about that queue, where customers arrive, get in line, get served and leave? Such a queue is usually denoted by m/m/1. These three numbers m, m and 1, they represent the type of arrival process, the type of departure process and number of people serving this queue. That is, number of people who are providing the service to the people who are waiting in the queue. So m/m/1 is a queue where arrival process is Markov, that is, the inter-arrival times are independent of each other and they follow the exponential distribution, and the departure process is also Markov, and there is one person serving these people who are standing in the line. So this type of continuous time Markov chain can be transient or it can be recurrent. When I say this type of Markov chain is transient, that means that if there are a few customers at this time, then you will never revisit that state. Number of customers will continue to grow. And if I say that this type of Markov chain is recurrent, that means if there are few customers, say 5 now, then there will be time again in future when there will be 5 customers, and again there will be many instances of time when there will be 5 customers waiting in line. That is, this chain will not grow to an infinite size. The people will continue to get the service and this queue will not grow indefinitely. So this type of Markov chain, which is denoted by m/m/1, can be transient or it can be recurrent, and the condition for this decision is based on arrival rate and departure rate. So this type of continuous time Markov chain denoted by m/m/1 is transient if mu is smaller than lambda. That is, arrival rate is larger than departure rate. If that's the case, then the queue will continue to grow and you will have a transient queue. It's not always the case that there is one person serving a line. There can be more than one, and if any of those people is free, then the person standing at the head of the line, the next person goes to that available person, gets served, and then he leaves. So that type of queue is called m/m/k, where k represents the number of people serving this line. So this type of continuous time Markov chain can be transient or recurrent depending upon this condition. If k times mu, and mu is the departure rate applicable for each customer service representative. So if k is the number of people serving the line, k mu time is the effective total departure rate. If that departure rate is smaller than the constant arrival rate, then we have a transient m/m/k queue. And if this number is larger, that is the effective total departure rate is larger than the constant arrival rate, then we have a recurrent queue which will never grow indefinitely. A logical extension to this scenario, a theoretical extension, is that we have an infinite number of customer service representatives. There is one line, there are people in the line, and there are infinitely many people serving this line. So that type of line is m/m/infinity. If that's the case, then this type of continuous time Markov chain is always going to be recurrent. It can never grow indefinitely. So it doesn't matter what is the arrival rate, as long as arrival rate is finite, as long as the departure rate is more than 0, no matter how small, if there are infinite number of people serving this line will be recurrent. So m/m/infinity queue is never transient, it is always recurrent. So if a continuous time Markov chain can be modeled by a variation of general birth and death process, we can use the associated lambda n's and mu n's to decide if this Markov chain is transient or recurrent. Now suppose a continuous time Markov chain is recurrent. All the states are visited again and again. We don't know at what time, but they do get visited again and again. In that case, we can talk about probabilities, the stationary probabilities. What is the probability of this random process being found in a certain state in the long run? There could be an initial transitory behavior where the Markov chain takes time to settle down, but once it has settled down, what is the probability of this Markov chain, the continuous time Markov chain, showing its state to be a certain state? And we can find these stationary probability distributions by following a simple procedure that I'm just going to outline. You can find the details in any good textbook. So the value of stationary probability, and so if a recurrent Markov chain has a stationary probability distribution, then we have different numbers associated with different states, and these numbers do not change in the long run. So if these numbers do not change, then the rate of change of these probabilities will be 0. That is, in the long run, when t has gone towards infinity and everything has settled down, then rate of change of finding n people at time t is going to be 0. We can use this equation and we can find the stationary probability distribution associated with general birth and death type random process. So if we find that and we continue to find stationary probability values, then this is the general expression which gives us probability value for stationary probability distribution associated with state n, as this expression shown on your screen, which is pi 0, the stationary distribution associated with state 0, times a lot of lambdas in the numerator and lot of mu's in the denominator. Please note that this expression starts with lambda 0 and the denominator expression starts with mu 1. This expression in the numerator stops at lambda n minus 1, but this continues to go on till mu n. So stationary probability values associated with all states can be expressed as some factor which multiplies with pi 0. So all other probabilities can be expressed in terms of pi 0. So how do you find these numbers? If you know pi 0 and you know associated mu's and lambdas, you can find pi 1. Then you can find pi 2 and pi 3 and so on. It's very easy because you know that summation of all these numbers, pi's associated with different states, is going to give you a sum of 1, because sum of all these probabilities is going to 1. So you sum all these numbers and take pi 0 outside, which is common, equate it to 1, and then you take that summation and take it below 1 in the denominator, you get your pi 0. You use that fact and you use that value of pi 0. So this is where you divide all this expression, and this is the infinite summation of all these expressions, and when pi 0 is outside, you take the inverse, and this is the expression for a stationary probability value associated with state n when you are modeling a general birth and death type process where birth rates are lambda 1, lambda 2, lambda n, and death rates are mu 1, mu 2, mu n. Let's apply this procedure to a simple case of continuous time Markov chain, that is m/m/1 type Q. In that Q, the arrival rate is constant, which is lambda, departure rate is constant, which is mu, and you can find that infinite summation, and that is easy to find because all these numerators and denominator terms are same. So if you apply these formulas to this case, you get an expression for pi n, the stationary probability value associated with state n, and it comes out to be this simple expression. If you know the probabilities associated with all the states in m/m/1 Q, then you can find the expected value of this length of Q. Remember, if this Q is in state n, then there are n customers waiting. So what is the expected number of people waiting in the line? That is the expected value of this stationary probability distribution. You can find this expected value simply by summing these probability values, multiplying them with n. So n times pi n summed over all possible states is going to give us this simple expression, which is lambda times mu minus lambda. And this will give us a positive meaningful number if this mu, the departure rate, is larger than lambda. Then this number, a small positive number, which will divide this lambda, and it will give us an expected length of q, the stable, stationary, long-term expected value of length of m/m/1q. So this general birth and death type random process can be used to solve many situations where transitions occur, and they occur at any possible value of time. For these type of unpredictable random phenomenon, we apply this continuous time Markov chain analysis and find interesting values of stationary probability distributions, expected length of line, and other quantities of interest. You can certainly apply this analysis to other queuing models, m/m/k or m/m/infinity. And you can talk about other problems where transitions occur at any possible time, and you want to model this behavior with continuous time Markov chains. There is another extension of analysis of unpredictable time-varying random phenomenon where the transitions happen at any time, but transitions are not in a finite number of states. The things change, but they change smoothly. So the value at first time instance t1 can be any real number, and value at a next time t2 could be any other real number. Those type of time-varying, unpredictable random phenomena are quite difficult to analyze, but there is a rich collection of material, a rich collection of literature that deals with these type of continuous time, continuous state random processes. I hope I have given you enough background to study those random processes on your own. But as far as contents for this course is concerned, it is limited to analysis of continuous time Markov chains where transitions happen at any possible time, but the transitions happen only in finite or countably infinite state space. With this, we have come to the end of this series of lectures. In the 45 lectures that we went through, I talked about many interesting real-life examples where unpredictable phenomena could be analyzed in more precise manner using tools of probability theory. I gave you interesting examples so that you can find this course interesting. I hope that you will study hard and try to apply these ideas that you learned in your academic pursuits as well as your real life situations. I thank you very much for being with me for these 45 lectures, and I wish you the very best in your life. Thank you. Khuda Hafiz.